Okay, so the given question is week 10, question number 14. Okay, so the RL circuit is given. Okay, so L 1 Henry, R 2 ohms. So U of t is given, Y of t is given, and C is 1 Fermi. Okay, so write the dynamic equations. Okay, L, R, and C are given. Initial conditions are also given. Y of t naught is equal to 1. Okay, so 1 volt. Then this will be V naught of this will be V naught. Okay, then V naught of Y naught Y dot of T naught, that is 0. Okay, so assuming input is U is equal to 0 and T naught is equal to 1. Initial condition starts from 1 second. Okay, then find Y of t at t is equal to 2 seconds. This is the question, correct?
Yes, sir.
Yeah. So the first thing is you have to find the output. Y of t means V naught. Okay, V naught of t at 2. Okay, so at 2. That means what? You have to find output at 2 seconds. That is our question. Correct? What is that output here? So that output is nothing but VC of 2. Am I correct? Voltage across the capacitor. Correct?
Yes, sir.
Yeah. So you can write down the equations. First, dynamic equations are nothing but what? Either KCL or KVL equations. Okay. So any equation is fine. KCL equations or KVL equations. Okay. So let me write down the equations. Okay. Mm, let's say we apply the KVL equations. Okay. Let's say these are the uh, two meshes. Okay. Then let us say this is I1, this is I2. Okay. What is the equation for I1? Let's say if you consider this is plus minus plus minus. Okay. So then what is the equation? Minus U of t plus L di 1 by dt plus R I1 plus 1 by C, that is nothing but 1 by 1 integral minus infinity to t. Okay, I1 minus I2 dt equal to 0. Am I correct? Let's say this is for mesh 1. Okay, what about for mesh 2? Mesh 2 equation is like this. Okay, this is plus, this is minus. Okay, so plus V naught. Okay, and plus 1 by 1 integral minus infinity to t I2 minus I1 dt. Is this clear?
Yes, sir.
These are the two KVL equations at mesh 1 and mesh 2. Okay. Now what you need to do is you need to find uh, these two are given. Okay. V naught, Y means what? Output. V naught of 1 is given. Okay. T, because T naught is 1. That is 1 volt. Okay. V naught of V naught dot of 1 is also given 0 volts. Okay. Uh, what you can do is from here you could write V naught. Okay, so you have to find uh, V naught at 2 seconds. This one. Okay, so that will be like I can write minus infinity to, let's say, 1 by 1. I'll keep this one as it is. Why? Because that is 1 by C parameter. T. I1 minus I2 dt. Correct? Let me say this is 1, this is 2. Okay. What I can do is, what is the best way? So you have to find the output. This is V naught to dt. V naught of t. Okay. Output at 2 seconds. Okay. V naught at 2 seconds. Okay. So equation 2, I can write it like this. Uh, uh, we need to get to, finally, we have to get the V naught expression. Okay. Right. At 2 seconds. Okay. So what we can do is, V naught expression I want. Can we convert everything into, mm, let me explain. We have given initial condition. Initial condition not V naught is given. Um, what if you take the Laplace transform? Let me try. Let us keep like this. Let us give it a try. Uh, what if you take the Laplace transform of everything? Initial, because initial input is given at t naught is equal to 1. Uh, so we have to find at t is equal to 2. Mm, let me take like this the problem. So L is equal to 1 h. So another way I can write it is as Ls. Okay, this will be yes, this will be 2. This will be 1 by s. This is the y of t. No, 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 no. So this is another way. This way also we should get the answer. This will be like v y of s.
Sir, I have done through
Yes.
this method.
Sorry.
Sir, I have done through this method and then I got the equation s square plus 2s plus 1 is equal to 0.
What is it? S square plus 2s plus 1. What is it meant for? Uh,
Sir, when the
yes, yes. Yeah, yeah. Tell me. This is the first one is the time domain method. Okay. So we keep everything in the time domain parameters. So second one is called as the S domain. Okay. We convert everything into S domain and try to solve the problem and get back into the time domain. Why? Because we wanted to convert everything into time domain at the end. Okay. So this way, what we can do is, let me tell you. Okay, so since y of t naught, okay, y of t naught and v of t naught are given. Uh, I think everything we need to convert it into, uh, since initial conditions are given, okay, in any way we need to get the answer. Initial conditions are given. This way, what have you tried? What you are trying to find here?
Sir, I was basically stuck. Like I got the first I wrote ut is equals to L di by dt plus ri plus yt. Then I put the value of I, and I got the second order equation. And then
Sorry, ut is equal to,
ut is equal to L di by dt
yes, correct,
plus ri
plus correct.
plus yt.
Okay,
Then I put I is equal to c dy by dt.
I is equal to c d dy by dt.
Yes, v that y t naught is equal to v naught.
That is also correct. So you will get everything into, so you'll get d square y by dt square. That is also correct. What is the issue in this way?
Sir, I basically did not know what would be the approach like to get the answer. I got the equation, but I don't know
No,
the
no,
approach.
your approach also correct. So in any way, you should get the same answer. So let us say if you keep it like that, u of t is equal to L C, correct? D square I by dt square plus
Plus
RC.
r dy by dt.
I'm sorry, this one. RC dy by dt plus y.
Okay.
Okay.
Yes,
So
sir.
now if you take the Laplace transform on both these sides, okay. So either you can solve this equation directly.
So first I put the values like L is equal to 1 Henry, R is equal to 2 ohm, and C is equal
No,
to 7.
values are fine. So L is 1 and R is equal to 2. C is equal to 1. Okay, okay, let's fine. So U of t is equal to 1 because L is equal to 1, C is equal to 1, R is equal to 1, R is equal to 2. Okay. So this will be 1 d square y by dt
dt.
square plus RC. That will be 2 dy by dt plus y. Okay. So now this is like second order, okay, differential equation with constant coefficients, correct?
Yes, sir.
Okay, so generally the solution would be like, okay, so y of t will be yh of t plus yp of t. Am I correct?
Yes, sir.
Yeah. So where yh of t, let us say this is 1. So yh of t is nothing but the solution of, okay, d square y by dt square plus 2 dy by dt plus y equal to 0, homogeneous part.
Yes, sir.
Okay, it will be like d square plus 2 d plus 1 multiplied y. Okay, so the roots will be like d square plus 2d plus 1 equal to 0. Okay, what are the roots? d1 comma d2 is, what are the roots? It will be d plus 1 whole square, correct?
Yes, sir.
Minus 1 comma minus 1, correct? So then your yh of t will be, okay, so k1 e power minus 1t, okay, because both the roots are same, both the roots are same, what we can write is k1 plus k2t, correct? E power minus t. Am I correct?
Yes, sir.
Yeah. So that is one solution. Okay. Next, yp of t will be like, okay, yp of t, what you can take is the, you take the form of the y of t. you take the form of the y of t. Okay. So that means yp of t will be similar to u of t. You got it?
Yes, sir.
Similar to u of t. Here, uh, u of t information is not given. Okay, so generally u of t can be like a DC source. If it is a DC source, we take that is as some constant. Okay, okay. If it is AC source, we'll take it like a cos. If it is AC source, like sine omega t, we take it like a cos omega t plus b sine omega t. Okay, that kind of form we will take. Okay, so time being here, take the source as DC source. DC source means constant source. Okay, if it is constant, now consider this equation. So what you get, a is equal to, what is the derivative? We will get 0, 2 times derivative plus 0, correct? Plus uh, yp. Am I correct? No, no, no,
Yes. Sir, in
no,
question
no.
u
Just a
is
minute.
equal to 0 is given.
No, no. 0 at 1 second. Initial
Yes.
condition.
Yes.
Assuming input u is equal to 0, uh, input to u is equal to 0, p0 is equal to 1. Oh, okay, okay. Then we can take it directly. This is not needed. Okay. So if that is 0, then yp is also 0. Okay. If yp is 0, what is our final solution? So from 1 implies y of t will be yh of t only. Okay. Plus 0. Correct? So finally, y of t will be yh of t, which is nothing but k1 plus k2t e power minus t. Okay. So this is the final equation. Let me write it again. So y of t is equal to k1 plus k2t e power minus t. Okay. And now initial conditions are given. What are the initial conditions? Y of t naught is 1 volt. Okay, where T naught is 1. Okay, then y dot of T naught is equal to 0
Zero.
volts. Okay, so now just give me a minute. Yes, you want something? I'm taking live session. Half an hour. Yeah. So now we have two initial conditions. Okay. So when you substitute first initial condition, y of T naught, that is y of 1, which is nothing but k1 plus k2 multiplied 1, okay, e power minus 1, okay, equal to 1. This is one condition. Then y dot of t naught, correct? So y dot of t naught is 0. What is y dot of t? Y dot of t first. Let me write it here. What is y dot of t? That is nothing but from this equation. You can take the derivative, correct? So
Yes, sir.
that will be like k1 plus k2 e power minus t plus, okay, then k1 plus k2t minus 1, sorry, e power minus t, correct? So this is, let's say, a, then y dot of t naught, okay, that is nothing but y dot of 1, which is nothing but, so k1 plus k2 e power minus 1 plus k1 plus k2 multiplied 1 minus e power minus 1 equal to 0. This is B. Clear?
Yes, sir.
Okay. Now from A and B, okay, so solving A comma B. Okay, you can find the values of K1 and K2. Correct?
Yes.
Once you have K1, K2, again from here we have y of t expression. You substitute those. So K1 expression plus K2 expression multiplied t e power minus t. So once you have this, okay, so final answer, substitute t is equal to 2. Y of 2 you need to find.
Oh, K1 and K2 is equal to 1.
You're getting K1, K2 are 1.
Yes, sir.
Yeah, so 1 plus 1, please check. And this 2, then e power minus 2. That's your answer if you calculate it. Got it?
Yes, sir.
Yeah. So the key point is this one. So second order differential equation. When you have second order differential equation, so this is the general form. That is one way. Okay. The other way is you don't need to getting into this form. Directly you consider this equation. Okay. Consider this equation. Substitute. I mean, convert that into apply the Laplace transform. Okay. Apply the Laplace transform and get the y of s expression and take the inverse Laplace. You should get the same equation. Is this clear?
Yes, sir.
Yeah. This is one way. Even this way is also right. I'm taking I1, I2, and again, I'll end up with your equation only. This equation only. So any way is correct. Okay. Any doubt?
No, sir, it's clear.
Hmm. Yeah. So we'll check this design assignment problem. So design assignment 2. So if you see the question 1, okay, so design assignment 2. So question 1 is, so unity feedback system, unity feedback closed loop system with the open loop transfer function g of s is given. Okay, so that will be like k by s square multiplied s plus a s plus b. Okay, these AB values are given for individual student differently. A is greater than 0, B is greater than 0. Okay, so this is given. Okay, now we need to design a cascade compensator using the Bode plot, using the Bode plot. Okay, that compensates the following specifications. Okay, what are the specifications? So the first specification is the steady state error. Okay, so a specific value. Okay, for the parabolic input. Parabolic input. Okay, so the value is given different value for each student. Okay, then bandwidth. Okay, so a specific value again for different value for different student. Then phase margin is also given. Okay, so these AB values, these ESS, bandwidth, phase margin are different. Okay, so finally we need to design this cascade compensator. Okay, using this Bode plot. Okay, which satisfies these specifications. So the ESS should be this much, the bandwidth should be this much, and phase margin should be this much. Okay, so first of all, let us consider some sample values. Let's say A is equal to 16, B is some 22, ESS is 0.025. Okay, so bandwidth is 31.69 radians per second. Okay, let's say phase margin is some 38 degrees. Okay, so whatever the values you have, you can replace those values. Okay, now we'll see how to design this cascade compensator. Okay, so first, the open loop transfer function. Okay, so g of s is given. Okay, so that is substituting a and b values, s square plus s plus 16, s plus 22. If we substitute a and b values, okay. So the after the cascade compensator, okay, the let's say cascade compensator is the C of S. Okay. Then compensated loop will be L of S equal to C of S multiplied G of S. Okay. So we have to design this C of S. Okay. Once we design this C of S, we have to design this C of S to meet this ESS bandwidth and phase margin requirements. Okay, so let us start with one by one. Okay, so the first one is, okay, so first gain k. Okay, so from the steady state requirement, let us find the gain k from ESS requirement. Okay, so what is the ESS requirement we have? So ESS requirement is 0.025. Okay, so now here a critical point is given. Okay, we have type 2 system. We have type 2 system. So for type 2 system, we know the acceleration error constant. Okay, so limit s is tending to 0, s square g of s, s square g of s. Hope this is clear. Okay, then so let us substitute the values. K equal to, okay, limit s is tending to 0, s square g of s is k by s square multiplied s plus 16, s plus 22. Okay, so and if you take s is tending to 0, these two gets cancelled. S is tending to 0 leads to k by 16 multiplied 22, that gives k by 352. Okay, that is the acceleration error constant. This we know from the starting chapters. Okay, then once we have ka, okay, so we know from the starting weeks for parabolic input. So our steady state error in terms of acceleration error constant is like this: ES is equal to 1 by KA. Okay, so that is nothing but we have this K by 352. If it gets reversed, 352 by K. Okay, now which is equivalent to ESS. ESS is given is 0.025, which leads to K is equal to 14080. Okay, then our uncompensated uncompensated plant for design, that would become G of S equal to, so K by 14080 by S square multiplied S plus 16 S plus 22. Okay, this is the uncompensated system plant transfer function. Okay, so that is first part where we are finding using ESS we found the K. Okay, next. So, uncompensated frequency response. Okay, so uncompensated frequency response. Okay, so for desired bandwidth, desired bandwidth. Okay, so here basically we are looking for the uncompensated frequency response for the desired bandwidth. What is basically desired bandwidth is, so desired bandwidth, what we need is this much, 31.69 radians per second. Okay, so basically what does it mean? So bandwidth is almost equivalent to omega c. Okay, so what we want is, we want the gain crossover frequency. So gain crossover frequency. Okay, gain crossover frequency to be, so omega c is equal to 31.69 radian per second. That is our need. Okay, so next we'll find both magnitude and phase for this frequency. Okay, so first magnitude. Okay, so we have uh, we have g of s is equal to what? 14080 divided by s square multiplied s plus 16 s plus 22. Okay, we'll find both magnitude. So g of j omega c, and we'll find the angle also. G of j omega c, where omega c is nothing but 31.69 radian per second. Okay, so basically what is this? So uh, this is 14080 divided by, so omega square root of omega square plus 16 square root of omega square plus 22 square. Okay, so if you substitute everything, okay, so that would be like 14080 divided by omega square is 31.69 square root over 31.69 square plus 16 square, 31.69 square plus 22 square. Okay, so if you do all these calculations, okay, you will get that is as approximately 0.01024. That is the magnitude. So once we have that, 20 log mod g of j omega c is, so that is approximately 20 log 0.01024. So which is almost equivalent to minus 39.8 dB. Okay. Similarly, if you check this, the this is the magnitude and this is the phase. So the phase angle would be like, so the numerator is 0, denominator is minus 180 because s square we have. Then tan inverse, we have omega by 16. Then minus tan inverse, we have omega by 22. Okay, from here, from this. Okay, so then we can substitute omega c here at every point. Okay, if you substitute them, so it will be like minus 180 degrees minus tan inverse 31.69 by 16 minus tan inverse 31.69 by 22. Okay. So minus 180 minus this will be like some 63.25 degrees. This is some 55 degrees, where you will get the value as minus 298.5 degrees. Okay, this is the phase. Okay, this is the magnitude. Okay, these values we need. Okay, so now what basically we require, we have L of S. Where is L of S? This one, which is nothing but C of S, G of S. Okay, so we need, so we have L of S is equal to C of S, G of S. Okay, what we need is, so angle L of J omega is should be greater than minus 180 plus 38 degrees. Okay, so that will be equivalent to minus 140 degrees. What is this 38 basically? This 38 is nothing but the phase margin, given phase margin. Okay, 38 is nothing but given phase margin. Okay, so this is given phase margin. Okay, after compensation, this is our compensated loop. Okay, so after compensation, we require phase margin of 38. It means that the phase of this compensated should be minus 180 plus 38, which is equivalent to minus 142 degrees. Okay, now since L of S is C of S, G of S. Okay, so the compensation need to be boosted. Okay, so the required phase angle boost from the compensator C of S at particular omega C is, it should be how much? The pi required is nothing but, we have minus 142 here, and this is after compensation, this is before compensation. Okay, so you just need to subtract. Okay, minus 142 minus of minus 298.5. How much it is? 156.5 degrees. This is what we need. Okay, the compensator should boost the pace uh, by 156.5 degrees. Okay, also it has to boost this much. Okay, also it has to, the compensator has to provide, the compensator has to provide. Okay, so plus 40 dB gain, plus 40 dB gain to rise the magnitude from minus 39.8 dB to 0, to 0 dB. To 0 dB. Okay. So this basically we have to provide two things. Okay. So the compensator, it has to do two things. So one is to provide a phase requirement of this much and to shift the magnitude of this much. Okay. So this basically motivates these both requirements. Basically motivates the two-stage lead compensator. two stays lead compensator. So what we do in the lead compensator basically, okay, let us consider that is the third step. So two stage lead compensator. Okay. So C of S. Okay. 1 plus TS divided by 1 plus alpha TS. This is the lead compensator for a value of alpha should be between 0 to 1. When we say two stays, okay, both will be in the cascade. Both will be in the cascade. In the first stage, okay, we'll have the lead compensator that will 1 plus TS by 1 plus alpha TS. Okay. So then here for this, we'll have from the theory, so it can provide at max phase angle of 1 minus alpha by 1 plus alpha. Similarly, we have maximum frequency is okay 1 by t at an angle alpha. Okay. Then you'll have a C lead of j omega is 1 by root alpha. Okay. For single lead compensator, so these are the design parameters. Design parameters. So you have to find the pi max, omega, and t also, alpha and t also. Okay. So now since we have uh, two identical stages, okay, let me write it here. So we have two identical stages. Okay. At omega is equal to omega m. Okay. So then we need phase boost of 2 pi max. That is 1. Okay. Then mod C of j omega m equal to 1 by alpha. If you keep them two side by side, okay, so that will become 1 by root alpha square. Okay. Then let us choose this omega C as 31.69 radians per second. Okay, this is what we are going to do for two identical stages. Okay, so we need a phase boost of this much and a magnitude of this much, and we are choosing the frequency of 31.69. So we have to find alpha first. Okay, then we have to find t. Okay, so we have to find two things. Okay, find alpha and t. This is the requirement. Okay, first let us find the alpha. Okay, first find the alpha. Okay, let us say this is step 4. Okay, so uh, we want, okay, let's say finding alpha from magnitude requirement. Magnitude requirement. So what we want is at omega c, we want, okay, the compensated loop magnitude of L of j omega c, okay, which is nothing but magnitude of C of j omega c, g of j omega c should be equivalent to 1. Okay, let me write it. Should be equivalent to 1. Okay, so this I can write it like approximately, okay, C of j omega c magnitude approximately is 1 by alpha. Okay, so this implies Okay, so 1 by alpha, okay, C of j omega c, we have already calculated. Okay, so we have already calculated C of j omega c, this one. Okay, 0.01024, 0.01024, which is equivalent to 1. So we can calculate alpha as 0.01024. That is our alpha. Okay. Now you can compute this 1 minus alpha by 1 plus alpha, because we have this pi max. Okay. So 1 minus 0.01024 divided by 1 plus 0.01024, which is approximately 0.9797. Okay. So then pi max is sine inverse 0.9797, which is almost 78.4 degrees. Then 2 pi max, because we have two identical stages. This we need. Okay. So which is equivalent to 2 multiplied 78.4 degrees. So that is 156.8 degrees. Okay. So then let me put this on this side. Okay. Then we have, okay. So then compensated loop. Then compensated open loop phase, open loop phase at omega c. Okay. So that will be like L of j omega c is nothing but angle j omega c plus 2 pi max. Okay. So that is minus 298.5, which we have already calculated here, plus, oh, I'm sorry. Yeah. So this one plus the 2 pi max plus 2 pi max is this one 156.8 degrees, which is equivalent to minus 141.7 degrees. Okay. Now phase margin. Phase margin PM equivalent to 180 minus 141.7, which is 38.3. Okay. So requirement is 38 only. Our requirement is 38 only. So it is matching. Okay. So that is how we are finding the alpha. Okay. We found the alpha. For that, the phase margin came out to be 38.3, which is greater than 38. Okay. Next, we need to find the T. Okay. Let's say step 5, determining T. Determining T. Okay. So we know that omega m is 1 by T root over alpha. Okay. So this implies T is equal to 1 by omega m root over alpha. Okay. So we know already omega m is 31.69. Alpha we got as 0.1024. Okay. So then we can write T is equal to 1 by 31.69 root over 0.01024. Okay. So which is approximately 0.312 seconds. Okay, so that you can check that. Okay, you got T, you got alpha. Okay, now the compensator. So this one compensator is this C of S. Okay, where we can find the S and the alpha TS also, that we can check here. So we can calculate the zero. Okay, zero, that is yes, minus 1 by T. Okay, you'll get minus 3.21, and pole is okay minus 1 by alpha T, which is nothing but you can substitute minus 1 by alpha is 0.01024 multiplied 0.312, which is nothing but minus 313. Okay, now the compensator. So the compensator C of S is, substitute the values, 1 plus 0.312S divided by 1 plus 0.00319. Okay, yes, whole square. Okay, so then compensated open loop transfer function. Compensated open loop transfer function. So that is L of S. That is nothing but C of S multiplied G of S. Okay. So which is nothing but 1 plus 0.312S divided by 1 plus 0.00319S whole square multiplied 14080, the G of S, S square multiplied S plus 16, S plus 22. Okay, these two. This is the compensator, and this is compensated open loop transfer function. Okay, if you want, you can also verify. You can also verify the things. Okay, you should get the same answer. Okay, let us do the verification. As of now, any queries? Let us do the verification also. Then you can ask me the queries. Okay. So finally, these are the two things. Let me copy this. Yeah. So these are the two things. You can do the verification. Okay. So first one is steady state error. So steady state error. Okay. So since C of 0 is equal to 1, compensator 0, when you substitute S is equal to 0, 1. Okay. So the KA limit S is tending to 0, S square L of S. Okay. If you substitute them, so C of 0, K by, sorry, K by AB. Okay. So that will be like 14080 divided by 1622. Okay, which is equivalent to 40. Okay, now steady state error is 1 by Ka. Okay, 1 by 40. So which is equivalent to 0.025. Okay, it is satisfying the given value. This is the given value. Okay, next. So next is bandwidth. Okay, so bandwidth we have designed for L of j omega c. Okay, equal to 1 at omega c is equal to 31.69 itself. Okay, so hence bandwidth will be approximately equal to omega c is equal to 31.69 radians per second. This we don't need to verify because that is our choice itself. Okay. Then next phase margin also we have verified. Phase margin. So what we got phase margin as 38.3. Okay, which is greater than or equal to 38 already. Okay, so this is also getting satisfied. This is also satisfied. Okay, so this is the problem. So let me go through roughly once again the steps. Then you can ask me if you are having any doubt. Okay, so the basically assignment says that the open loop transfer function g of s is given. Okay, g of s is given, and AB values are different values for different students. And we have to design this cascade compensator using the frequency response Bode plot, okay, to meet these three specifications: ESS, bandwidth, and phase matching of these values. These are the values we have chosen. Okay. So first we are finding the, in step one, we are finding the gain K for this steady state error using the acceleration constant as well as the ESS equation for the earlier modules. Then we are finding uh, the gain crossover frequency omega c for the given bandwidth. Okay. Then for these expressions, we are finding the magnitude of open loop transfer function and phase. Okay. So based upon these, we are finding the compensated system. Okay. How much it has to, how much phase it has to satisfy. Okay. To meet these two magnitude and phase requirements. Okay. So then this is the phase requirement the compensator has to satisfy. Okay. And this magnitude requirement, phase requirement of 156.5 and magnitude requirement of 40 almost, going from -40 to 0. Okay. This motivates the choosing the lead compensator. Okay. So basically this is the lead compensator. When we put them into cascade, this is the expression. So there, these are the design parameters: I max, omega m, and C lead. We have to find the alpha and T. Okay. First, when we these are for single compensator. So when we have this two identical, when we put them two identical compensator in cascade, okay. So we have these expressions. Okay. So we can find alpha, okay, to meet the requirements, and we can find the T also. Okay, finally, this is our compensator, two stage compensator, and verification also. Okay, so are there any queries? This is how you have to proceed. Do you have any queries? You can go through these values so that you will understand all these steps. Are there any queries?
No, sir.
Yeah. Okay, we have 15 minutes time. If you have any other doubts, you can ask me. I'll stay for another 15 minutes time. If you don't have any doubts, we will close here. Will there be any uh, mock for the end exam? I think there will be no mock. I think I told you the uh, pattern also. We'll have multiple choice questions, uh, short comprehensive questions like fill in the blanks. Okay. And you have multiple answer selection questions. I think that's it. So the test is totally computer based. It's no need to rough work you can use, but you don't need to submit any written part, handwritten part. So for the next live, what we can do is, okay, so you can collect all the particularly these uh, questions from the practice assignments and graded assignments. Okay, which you feel that okay, you have some doubts or you don't get answers or you don't understand some of the things, particularly these questions. Okay. So try to it is better if you mail us before the live session so that the time can be saved. Okay. So then we can discuss those questions only. Okay. In the next live, if needed, we'll discuss with sir and we can arrange for another live also. Maybe before uh, since the exam is on Sunday. Okay. Before Friday, we can either maybe on Thursday or Friday, we can have one more live. That depends upon necessity. Okay. Yeah. So thank you. So we'll stop here and continue in the next slide. Thank you.